On Thursday, we went over position versus time graphs. Okay, we did a few of each kind. We did some that were kind of all over the place. We did some that were linear. Okay, today we're going to start velocity versus time graphs. Okay, and again, this stuff, guys, is all reviewed from Science 10. There's not a single thing I'm teaching you about these graphs that I didn't teach you or that you weren't taught in Science 10. So hopefully it all seems familiar. Okay. If I have a velocity versus time graph and a position versus time graph of the same motion, are they going to look the same? Okay? They shouldn't. Okay? Do these two graphs show the same motion? On the left is the position versus time, on the right is the velocity versus time. Are they showing the same thing? These are graphs of exactly the same motion. Okay? Looking at the position versus time graph, what is this object doing? Right, moving at a uniform rate or a constant velocity, okay? In this case, in a forward direction, it would appear, all right? Could I figure out how fast it's going from that graph? I could. It's a linear graph, right? It's just one single linear function, okay? I would know that value to be 1400. I know this value here to be 100, and I know that this takes 5 seconds. Okay, so could I do this? Could I say m equals y minus b over x? Could I find the slope of that line? I could, okay? And the reason that that will give me velocity is because what I'm really doing is taking the final position, subtracting the initial position, and dividing by time, right? This would be my final position, this would be my initial position, and the 5 seconds would be the time. Okay. So if I do that, I'm going to have 1400 minus 100, okay, because b is down here at 100, okay, divided by 5 seconds. So 1300 over 5, I believe, is 260, right? I shouldn't do math in my head. Come on. Oh, I'm pushing the wrong button. I wonder if that's working. Okay, so 1300 divided by 5. Maybe I should do math in my head. Okay, 260. All right. Is this velocity versus time graph showing the same thing? It seems to me like it's showing an object whose velocity stays steady at 260 meters per second. Right? I mean, this is 250 right here. It's just a little bit above it. I'd say that's 260 meters per second for 5 seconds. Okay? So a position versus time graph and a velocity versus time graph can tell you the same story, but they look at it from different points of view. And so as a result, it looks very different in both cases. Okay? You'd be surprised how often I show a graph that looks like the one on the right on a unit exam as a multiple choice question. Okay, I'll show that and I'll say, what is this object doing? Okay, and I'll have like A, accelerating, B, moving backwards at a constant velocity, C, moving forwards at a constant velocity, and D, it's not moving. You'd be surprised how many people pick it's not moving because they see a horizontal line and our mind goes straight to horizontal line means nothing's happening. Is that true? Doesn't mean nothing's happening. Time is always going by. That's something. Okay? In this case, the velocity isn't changing. Okay? It doesn't mean it's stopped. It doesn't mean nothing's happening. It just means the velocity isn't changing. It's traveling at a constant velocity. Okay? Everyone all right with that idea? Okay? But that's like an easy multiple choice question that I can make up and throw at you, and it's just a graphical analysis question. We calculated the displacement on this graph. Okay, we just went final position 1400 minus initial position 100. We got 1300. Could I calculate the displacement from the velocity time graph? Definitely. Okay. Remember that average velocity is displacement divided by time. Okay. So if I want to find the displacement, what do I do with t? What do I do with t, guys, if I want to find d? Right, multiply it over to this side. Okay, so if I want to find the displacement, I've got to take the average velocity and the time. Well, the time is easy. The time is 5 seconds. Okay, I can see that clearly from the graph. What's the average velocity during this time? 260 meters per second. Okay, I just read that off the graph, right? Here's 250, here's 260, okay? It's going 260 meters per second for 5 seconds. Right? So I just go 260 times 5. Well, that sure better work out to be this number, because that's how I got the 260 before, right? Okay, so 260 times 5 is 1,300 meters in a positive direction. Okay? Now in Science 10, you probably memorized, it's the area under the line on a velocity versus time graph. How many people does that sound familiar to? Okay, now that works. Why does it work? Because the area under the line on a velocity time graph is the average velocity times the time. It's the manipulation of v equals d over t. Okay, now what if instead the line looks like, let's see, let me get to 600 for 6. Okay. Say the line looks like that. Does it still work? What is that object doing?
Accelerating.
It's accelerating, right? That line shows an object whose velocity is increasing. It went from 100 to 600 in 5 seconds. That's the fast object, okay? What it did. It went from 100 meters per second to 600 meters per second in 5 seconds. It is really cooking along. If I wanted to find the displacement, in Science 10 you learned, well, calculate the area of that triangle. Okay? Well, that works because if I do that, okay, I'm going to take the base, 5 seconds, which is the time, and multiply it by the height divided by 2. Okay, if I'm increasing my velocity at a uniform or linear rate, would my average velocity be halfway between my initial and final velocity? It sure would. Okay, if I start from rest and accelerate to 10 meters per second, my average velocity is 5. Half the time I was going slower than 5, and half the time I was going faster than 5. Okay, that's why it works. Okay, you're not really calculating the area under the line, you're just using this formula. You just may not have realized it. Okay? But you're still taking the time, the base, and multiplying by the average velocity, the height, or the height over 2 if it's a triangle. Okay? Everyone all right with that? What if there was a triangle with a rectangle under it? What then? So instead, I have a graph that looks like this. Did that object start at 0 meters per second? No, it was already in motion when this started. Okay, so that means that there's a distance it would have covered at a constant velocity had it not accelerated. Well, that has to be accounted for. Okay, so now I would find the triangle and the rectangle. Okay, I'm going, here's how fast, or far, sorry, the object would go if it didn't accelerate, and then I have to add on to that how far it covered while it accelerated. Okay. Everybody okay with that? These are the things that you would have learned in Science 10 for sure. Okay. Okay, what would the position versus time graph of this line look like? Yeah, a curve upwards, yeah, okay? A steepening curve is what we call that, okay? A steepening curve means it's going faster and faster, right? Because we talked about this last week. In the first 2 seconds, it only goes this far, but in the next 2 seconds, it went this far, and in the next 2 seconds, it went that far, okay? The only way to go farther is to go faster, okay? Making sense? Okay, so those two graphs, again, they tell the same story, but they look different, okay? Because they're telling it one from a here's how fast you're going, and one from a here's how far you went, okay, perspective. Right? Now, that is something that sometimes comes up on a test. Okay? I show you a position versus time graph, and then I say which of the velocity versus time graphs is showing the same motion. Okay? And then you've got to analyze and go, okay, what's going on in a position time graph? What does that look like on a velocity time graph? Okay? That's graphical analysis. That requires zero calculating. Okay? It is strictly patterns. Okay? Being able to see those patterns. Okay, questions so far? Okay, so this is a graph of a person running a race. This is not an overly fast person. Okay, so what's going on in like the first 5 seconds here? So this part of the graph. They're accelerating, okay? I mean, it's not a linear function because, well, it is pretty linear right here, but this first little bit, it's not. And that's because, like in track and field, if you're running a race, your first few steps are actually quite irregular. Okay, you're coming out of a set of starting blocks or something like that, and your first few steps are kind of off a little bit. But then once you get into your stride, you accelerate pretty uniformly until you get to your top speed. And it doesn't matter how hard you push, you cannot run any faster. So you run until either you get to the finish line, okay, that would be this part here, okay, or you fall down. Okay, either way, the end result will look like the last bit of this graph. Okay? How do I know that that part of the graph is showing them slowing down? Yeah, it's getting flatter, and I can clearly see that at the beginning of that part, they start at 8 and end at, yeah, that means they're slowing down, right? If I go from 8 to 0, okay, and that happened pretty fast, so they slowed down pretty quickly. Maybe there was a big padded wall at the end or something, okay, that they ran into. Okay, so this person accelerated for a while, and then they ran at a constant velocity of 8 meters per second for a little while, okay, which is not very fast, and then they slowed down and came to a stop. Okay. Why do I say 8 meters per second isn't very fast? Does that sound fast? Covering 8 meters per second? It's like probably from here to the wall in 1 second. That seems pretty fast. Do you know how fast the fastest man runs? 17 meters per second. Usain Bolt could get a speeding ticket in the playground zone if he's running. He's freakishly athletic though, okay? Dude's 6'7", okay? So when he's running at his maximum speed, he is covering this room, the hallway, and half of the next room. 1 second. Okay, like, don't get in that guy's way, okay? He's really, really fast, okay? Now, how long do you suppose his strides are if he can do that? Well, they're really long. Yeah, they're maybe not 17, but I mean, he's moving fast. His stride length at top speed is a lot. He can run the 100 meters in 33 strides. And that includes the first few little choppy steps at the beginning when he's coming out of the starting blocks. When he's at full bore, okay, he's like soaring across vast distance. It never looks like that on camera, okay, but it's what he's really doing. If you watch any of the Olympics this summer, okay, they had some really fast people, okay, in there, and it doesn't look like it because they're all fast. But if you were to put, you know, an average person in that race, they would look like they were like tied to something and trying to run in comparison, because they just wouldn't cover very much distance in every stride. Okay? All right, so yeah, Usain Bolt's graph would be like this. Except it would be shorter, like it would be, you know, there, okay, 9.48 or whatever it was that ran it in, okay? Making sense? This is actually something that like high-end athletes their data analysis and coaching is going to focus on their graphs. Okay? They're going to look at their stuff and go, okay, this is the weakest part of our race. We need to fix this part because we can improve how our graph looks and thus our performance in the race overall. Usain Bolt was a terrible accelerator. Okay? He was like a brutal out-of-the-block starter. Okay? Really, really bad. Like sometimes he would stumble. I don't know why he even used the things. Could have just stood there, okay, and still beaten everybody, right? But he was a terrible starter. They were always working on his acceleration, but he didn't really need to accelerate because his top speed was 2 meters per second faster than the next fastest guy. Okay? In almost every race he ever ran in, he came from behind to catch everybody. Okay? I mean, by 2/3 of the way through the race, he was way out in front, but it was just, he had to catch everyone. Once he got to top speed, everybody was doing this in the race. Always looking for him because they knew he was coming. Okay? So you can do data analysis for a lot of different things. Is basically what I'm leading to here. Like your skating speed in hockey, you know, or your cornering G-force and things like that, in, you know, in skating, or you know, especially for like speed skating, like, you know, short track, especially being able to get low enough and make those turns. All right, so on a velocity versus time graph, what can we read directly off the graph? Instantaneous velocity and time, yeah. Okay, and I say instantaneous velocity because I mean the velocity at this time. Okay, it's just like saying I can see the position and the time. I know where that person is at any moment in time. Well, on a velocity versus time graph, I know exactly how fast and in what direction that object is going at any point in time on the graph. Okay. Now, what can I get off of this graph? Well, I can get displacement. We learned how to do that last year. But I can get one other thing off of a velocity versus time graph. The acceleration. Okay, so if I go back to this first graph here. Okay, on this line here, we said this line shows an object that is accelerating. Okay. Did you learn a formula in Science 10 last year to calculate acceleration? Yeah, this one. A equals VF minus VI over T. Can I get those three things off of this graph right now? Okay, so the final velocity is 600 according to the graph. Okay. The initial velocity is 100, and that took 5 seconds. Okay, so 600 meters per second minus 100 meters per second is 500 meters per second, divided by 5 seconds is 100 meters per second squared. Okay? What does the squared mean? Does it actually mean I should square root this number to get the real number? No. It just means that when I did this, I actually went meters per second divided by seconds. Okay? Think fractions here, guys. Meters per second divided by seconds over 1. If I'm dividing fractions, what do I have to do to this? Flip it and multiply, right? Whoop, that's not what I wanted to do. Okay, so that means times 1 over seconds. What's meters times 1? Meters. What's seconds times seconds? Seconds squared. Okay. So that's where that comes from. You could also write meters per second, okay? We just don't usually say it that way. And we just say meters per second squared. All right? Okay, everybody all right with that? Okay. Now, I calculated the acceleration of this object. What did I calculate about this line? The slope. Yeah, I just calculated the slope of that line, right? Look at how this formula sets up. It sets up just like this one. It's because it is that one. Okay? A bunch of the formulas that are on our formula sheets are actually just the slopes of a particular graph. Okay? In this case, the acceleration is the change in velocity over time, or the slope of that line. Okay? I used b, 100, I used y, 600, and I used x, 5 seconds. Okay? Does that make sense? So I could, maybe on an exam, give you a graph and ask you, what does the slope of this graph represent? It doesn't require you to do any calculating, it requires you to analyze. Okay? I would look at this graph and I would say, all right, if I calculate the slope of this line, I'm going to have meters per second on the top divided by seconds on the bottom. That's going to get me meters per second squared. Those are the units for acceleration. Okay, the slope of this graph is acceleration. All right, that's graphical analysis. That's a skill we want you to have versus I got to memorize that on a velocity time graph, the slope is acceleration, the area under the line is displacement, and there's something else, and I don't remember what I don't want you to be there. Okay, use the tools. Okay, instead. Okay, so this is just what we just went over. Okay, why the area under the line is basically you just doing this. Okay, average velocity. Okay, times time. That's the area under the line. Okay, calculates displacement. Okay, this is a velocity versus time graph. I cut off the meters per second over here. I would like you guys to calculate for me for just run 1 and 2. Okay, so that's the blue line and the red line, so the first two here. Okay, I would like for you guys to calculate for me the acceleration and displacement. Okay, for just rounds 1 and 2. Okay, acceleration and displacement. Okay, is number one pretty straightforward? Do you actually have to do any work? What's the acceleration for run one? 1.28 meters per second squared. Okay, we just covered, guys, that the slope of a line on this graph represents the acceleration. Okay, it's the rate at which the velocity changes. That's what the slope shows. The slope always shows the rate of change of y, meters per second, over x, seconds. Okay, so the slope is 1.28 meters per second squared and 2.4 meters per second squared. Now, the tricky part here is number 2. Okay, calculating the displacement. Okay, especially for run 1, where the y-intercept is actually a negative number. Okay, I actually shouldn't have started with that. Let's not start with that one. Let's not do number 1, just because it's got that weird thing going on. Okay, so number for B. Okay, is my y-intercept 0? Okay, if my y-intercept's not 0, does that mean I have a tiny little rectangle under my triangle? It does. How high is that rectangle? 0.033 meters per second. Okay? Basically what we can't see very well here, guys, is that there is a tiny little red triangle underneath our red triangle. Now, how do I find the height of that triangle? Because I feel like I'm going to need that. I haven't been, oh, I am, okay. How do I find what y is right here at 0.7 seconds? That formula set up to calculate y? I think it is. And I'm pretty sure the x value where we want to calculate the height of that triangle is 7. Okay. If you get run 2, I want you to try and calculate the same thing for run 7. Okay? I'll be right back. So displacement for run 2 and run 7 to 7 seconds. Oh, I kept the recording on. Oh, nice. That'll be a nice long one. Okay, let's have a look at the red one here. If we want to calculate the displacement. Okay, first thing I need to find is what's the height of my triangle at 7 seconds, because that's where I stop recording, is 7 seconds for the red one. Okay, so if I want to calculate that, I'm just going to use this formula, and what am I going to substitute in for x? 7. X is the time, right? If I get a value like 7 seconds, I substitute that in for x. Okay, so what that's going to mean is 2.4 meters per second squared times 7 seconds plus 0.0333. Okay, so if I do that, so 2.4 times 7, okay, plus 0.0333. That's the height of my triangle. Or is it? That's where the line is. Is my triangle that tall? How much less is my triangle? You're nodding your head no, you know. Right, okay? My triangle is 0.033 less than that because I added on, according to this formula, that rectangle at the bottom. I don't want this rectangle at the bottom. I just calculated this whole line here, all the way from the x-axis. I only want from here to here, which means I don't even need that. Okay, so I actually only have 16.8, I believe is what it came out to, right? Yeah, 16.8 meters per second. That's the height of my triangle. Dead. Okay. Okay, so now I know the height of my triangle. Can I do the area of the rectangle and the area of the triangle?
This should be 0.7, not 7.
Oh, 0.7. Okay, so 1.68, sorry. Good eye. 1.68. Better?
Hopefully.
Hopefully? Yeah. Oh, no, but that'll change. No, we're good. Yeah. 1.68. Okay. Everyone with me there? Okay, can I calculate the area of the triangle and the area of the rectangle now? Well, what's the base for both of them? 0.7 seconds. Yeah. Now that we've established it's 0.7 and not 7. Okay, 0.7 seconds for each. Well, then I can go, all right, for the rectangle here, it's going to be 0.033. No, that's not right. That 0.168 is not right. Plus. Oh, yeah, it is. Yeah, sorry, it is. Okay, times 0.7 seconds. I'm all thrown, discombobulated. Okay, so that little rectangle is quite small, 0.02331 meters. And now I got to calculate the triangle. Okay, so that's going to be 0.7 times the height, which we established is 1.68 divided by 2. Okay, so 0.588 meters. Okay, and now I just add those two together. Okay, so there's the total displacement of that object to 7 seconds, 0.61 meters. Okay? Okay, now that you've seen it once, try it with run 7. That's the orange line. Or sorry, run 5. Sorry, run 5. The orange line, run 5. 5. All right, so on run 5, if I'm trying to find out the area of the rectangle and the triangle that exists for that line, okay, I'm going to have a orange rectangle that's going to go all the way to 0.7 seconds. I'm going to have this triangle that goes way above the graph, beyond anything we have, okay, and they're going to look like that. Now, what's the height of this orange rectangle? Yeah, 0.285. Okay, it's the y-intercept. That's where that line starts. Okay, and I know it's 0.7 seconds long, so I can calculate the area of that orange rectangle, okay, by simply going 0.285 times 0.7, right? And I'll have the area of that rectangle. That's kind of the easy part. All right, so 0.1995 meters. How does that come out to meters? I'm multiplying V times T, right? Meters per second times seconds makes the seconds cancel and leaves just meters behind, right? Okay, so I've got that. Then I've got to calculate the triangle for that orange one. Okay, so that triangle, I don't know how tall that triangle is yet because I haven't calculated it. But I do know enough to do that. Okay, if x is 0.7 seconds, I can calculate the height of that triangle. So I'm going to calculate the height of this triangle by going 7.61 times 0.7, and I'm not going to bother to add that on there because I just have to take it off after anyway, because that's the height of the rectangle. I only want the height of the triangle. Right? So 7.61 times 0.7. There's the height of my triangle, 5.327 meters per second. Okay, and we've already established that the base of that triangle is 0.7 seconds. So now it's just a matter of base times height over 2. Okay, dividing the height by 2 gives me the average velocity between bottom and top. All right, so 0.7 times that number there divided by 2. Okay, so the area of that triangle is 1.86. I add that to the 0.1995. Right, so that object goes a lot further. Okay? It goes over 2 meters, okay, during its acceleration to 0.7 seconds. Okay, is that ringing a bell a little bit? Okay, calculating areas. You maybe didn't go into it in this much depth in Science 10. It might have been a little bit easier, but okay, this is what we're headed towards when we do our acceleration lab next Tuesday. Or Monday, if you're ready. Sometime next week, early next week. Okay, let's say we've got this graph here. Okay, still a velocity versus time graph, but now it's not one linear function. Okay, can we still apply some of the formulas that we use to this graph? Okay, so instead of doing this stuff here, which I don't want to do, let me ask you to calculate this. Can you calculate for me the average acceleration over the whole trip for that graph? You might want to have your formula sheet out, as there is a formula that you did learn last year that does calculate average acceleration. You may have written it on the board a couple of times already today. Okay, last year, did we learn this formula? Okay, does that calculate average acceleration? It does. It doesn't say AAV, but it is. Okay, what's my final velocity according to that graph? 80 meters per second. Okay, minus 0. Okay, we started at 0 right here. Okay, and how long did that take? 60 seconds. All right, so that's what, 1 1/4 or 1.3? And I better indicate that that's positive because acceleration is a vector quantity and that was in a forward direction. Okay. Does it matter that the object didn't accelerate the entire time? It doesn't. I asked you for the average acceleration over the whole trip. Basically, I said, imagine the object did this. Okay, that's what you calculated. Okay, doesn't matter that it didn't actually do that. Okay, we calculated its average acceleration over the whole trip. It's no different than if you drove from Okotoks to Edmonton. Okay, you're going to have spots along the highway where you have to slow down. Okay, you're not traveling at the same. Maybe you had to stop and go to the bathroom at Gasoline Alley in Red Deer. Well, you stop for a little while. If I ask you to calculate your average velocity, it doesn't care whether you stopped, sped up, slowed down. It just cares what was your average over the whole trip. Okay. All right. What was the object doing between 20 and 50 seconds?
Constant motion.
Moving at a constant velocity of
40.
40 meters per second. Okay. Those are the kinds of things I could easily ask you on a quiz. Okay, I give you an irregular graph like this and ask for that. All right, now, calculate for me the total displacement over the whole trip for that graph. I would say we probably need to calculate the area of those three shapes, okay? Because they will represent the displacement of this object. During the first 20 seconds, the object accelerates, okay? Therefore, its average velocity would be half the height of this triangle. So we would simply go base 20 times height, 40 divided by 2. That should be 400 if my mental math is right. Okay? Now, for the second one, why did I extend the box all the way to the end? Is the end of that box still under the line? Then it still counts. Okay? Essentially what I'm saying here is all of box number 2 is how far this object would have traveled if it had just continued to go that fast. Then I'm going to add on to it the additional distance it traveled because it was accelerating. Okay? I'm accounting for all of it. Here's how far it would have gone if it just kept doing what it was doing, but I'm going to add on how much extra it went because it went faster for a little while. Okay? That's what we're essentially doing here. Okay? So the base of this one goes from 20 to 60, so that's a base of 40 and a height of 40. Okay? 40 times 40 is 1,600? Yeah? Oh, my mental math is sharp today. Okay, and then we've got that little triangle there. Okay, it's 10 on the base, and it goes from 40 to 80, which is 40. So 10 times 40, 400 divided by 2 is 200. Okay, so 1,800, 2,200 meters. Total displacement. Okay, that's pretty far in a minute. Things moving at more than 120 kilometers an hour on average as one fast snowmobile. I don't know if that's terribly realistic or not. Okay. All right, everyone follow what we did there. Okay. Did we do anything different? We just remembered that, okay, average velocity times time equals displacement. And then we did our best to find those average velocities, okay, and calculate the displacements from there. Right? That is exactly the kind of thing I would give you on a quiz, say, this Friday. Right? Now, on the board, I did put the 4 practice quizzes that are related to the stuff we'll be going over this week. Okay, there's some position versus time, some velocity versus time, and some acceleration stuff, which we'll be getting to by like Wednesday or Thursday. Okay, acceleration stuff is, I mean, what acceleration is, you learned in Science 10. We just add a couple more formulas, so it's really just algebra after that. Okay. All right, before you pack up, because we still got a couple of minutes here, I want to remind you that I got to hand back your vectors, your math activities. Okay, your vector assignments, don't forget about those. Okay, those are coming due on Wednesday.